morning, evening, and or afternoon, everyone, depending on your time zone, and thank you for joining us. So the closed captioning feature is enabled, so if you would like to use that, please feel free to do so. We also have the Q&A feature in the chat enabled, so if you have questions, please put them there and we'll get to them at the end of the talk. And then I also want to remind everyone that if you want to suggest future speakers in this series, we have a suggestion form on our website, and I'll put the link to that in the chat shortly. So without further ado, I'm so excited to introduce today's speaker. Dr. Tianhaozhe Sun is both a research scientist at the Geological Survey of Canada and an assistant professor at the University of Victoria. He's a geophysicist interested in tectonic and geodynamic processes at plate boundaries, especially subduction zones. And today he is joining us to discuss the evolution of slip and stress on the shallow megathrusts over subduction earthquake cycles. Thank you so much for joining us. And without further ado, the floor is yours.
Thank you so much for the introduction and invitation. Thank you so much. And thank you everyone for tuning in. So this talk today I'm going to give has benefited from the many collaboration I've done with the number of people shown here, and also including the interactions with a lot of my dear JFAST friends since the early days of my PhD work. And so without further ado, let's get started. So first, what do I mean by shallow megathrust? And I hope it to be clear that by saying shallow megathrust, I mean up deep of the seismogenic zone. So for a lot of places, if you are familiar with the definition of the segmentation by Professor Strong Lei, segmentation A to D, we are talking about the segment A here. And for some subduction zone, maybe also a part of the segment B. And this part of the fault tend to behave aseismically. It can host a stable sliding or conditionally stable sliding. But in some rare cases, they may participate in coseismic rupture of a large earthquake, or they may also nuclear some of the earthquakes themselves, for example, the so-called tsunami earthquakes. So over the past couple of decades, there has been a rapid advance of seafloor geodesy. And the different types of seafloor geodetic tools, such as seafloor GNSS acoustic and absolute pressure gauge, and also subseafloor borehole pressure, fluid pressure monitoring has been deployed at a lot of subduction zones. And these seafloor observations are also complemented by some very fortuitous cases where the presence of islands in the forearc or land area in the forearc, for example, in Sumatra and Ecuador, allow us to deploy and operate land-based GNSS at a short distance to the trench. So these observations, near-trench observations, are very important for us to understand the shallow megathrust behavior. And the overall picture is the wide detection of shallow aseismic fault slip, including slow slip events, both spontaneous or dynamic triggered events by large earthquakes, and also after slip following large megathrust earthquakes. And independent seismic observations also show that a lot of those aseismic slip events is accompanied by slow earthquakes. For example, tremor, LFE, and VLFE stands for very low frequency earthquakes and a very low frequency earthquakes. And some of those subduction zones are dominated by fault creep, aseismic fault creep at all depths. For example, the northern Hikurangi subduction zone off the east coast of the northern island of New Zealand, and also the Kyushu part of the Nankai Trough, southwest of Japan. But my focus today are those subduction faults that are able to host large magnitude 7.5 above earthquakes. And one example, a very recent example, is from the Alaska subduction zone. So here, 3 seafloor GPS stations were deployed before the 2021 magnitude 8.2 Chignik earthquake. And one of these sites, this site SEMI, is located right up deep of the coseismic rupture of this event. And a post-seismic survey of those sites about 2.5 months after this earthquake indicate a large cumulative coseismic and post-seismic displacements because of this event. And interpretation of this large displacement here, together with other other independent work to determine the coseismic slip distribution of this event, show that there's a large amount of shallow afterslip to the updip direction of the coseismic rupture here, up to amount of 1 to 3 meters. And we also see that this large shallow afterslip tend to drive a lot of numerous aftershocks, also in the updip direction. And a lot of those aftershocks showing the lower angle thrust faulting focal mechanisms. And this is an indication of the creep on the megathrust. And this kind of a relatively deep buried rupture followed by shallow aseismic afterslip at the shallow part, updip of it, has also been seen for some of those events here. And here I'm showing those 3 examples where the presence of the islands or land area near the trench allow GPS, land-based GPS to operate very close to the trench. And they help us to confidently resolve this shallow afterslip distribution. In all the 3 examples here, we see that the rupture itself is buried at some depths, but the aseismic afterslip probably goes all the way to the trench. And this presence of the shallow afterslip is also the true situation actually for the 2011 magnitude 9 Tohoku-oki earthquake, which is very well known for its large trench breaching rupture in the central area. So here, based on seafloor GNSS acoustic and also the differential bathymetry measurement, we can confidently resolve this large trench breaching slip in the central area of Japan Trench. But probably what is less recognized is that not too far to the north, the same differential bathymetry measurement suggests a lack of a large seafloor displacement, and therefore an absence of this large slip to the trench, to the shallow part. And after this event, Japan Coast Guard and Tohoku University continue to conduct seafloor deformation measurement along those seafloor GNSS sites. And 20 new sites has been deployed and operated by Tohoku University. And those seafloor GNSS stations provide important measurement over a decade by now for us to characterize the post-seismic deformation of this larger event, and for us to investigate the hydrogeneous fault behavior of the fault and also the regional Earth rheology. One important thing here I want to note is that in order to explain those post-seismic deformation, we need to introduce this shallow afterslip patch to the south and to the north outside of the rupture area. So, and this shallow distribution of the shallow afterslip patch to the 2 sides is also consistent with independent seismic observations showing the distribution of a lot of tremor and VLFE in those areas along the strike. And those events are also an indication of the megathrust creep. So the emerging picture is that the shallow megathrust can act as a soft barrier that tends to resist this trench breaching rupture, but it allows the fault to creep aseismically afterwards. And this is not to say that large trench breaching rupture cannot happen. For example, during the 2011 Tohoku-oki earthquake, and in the central part of Japan Trench, the dynamic weakening of the shallow part of the fault may allow the fault slip to go all the way and even peaking at the trench, as shown here. But for most of the earthquakes, the shallow part of the fault will behave as a soft barrier. So in some cases, if the strengthening of the shallow part is not strong enough, it may still allow some fault slip to go to the trench, but with a decreasing amount like the profile 2 and 3 here. But for most of the places, and has been confirmed by seafloor geodesy or near trench geodesy, we see that those earthquakes tend to be buried at a greater depths. And some seems to be even deeper in the along dip direction, taper to 0 even before reaching this soft barrier zone. And for very large event, for example, the magnitude 8.8 Maui earthquake, it is likely that some part of the fault is able to breach to the trench and for limited range in along strike direction. And whether this soft barrier can fully resist the shallow trench breaching rupture is very important for, it has important implications for tsunami generation. And this is something we try to address in this paper published a few years ago and titled Evaluating the Tsunami-genic Potential of Buried versus Trench Breaching Megathrust Slip. So the key consideration here is that even the trench breaching rupture is associated with a large, dominated by the large rigid body translation of the frontal wedge to enhance the seafloor uplift. The buried rupture scenario is associated with a large amount of elastic thickening of the upper plate and to form this big bulge on the seafloor to enhance the uplift. And systematic model tests show that a full resistance of the slip to trench, for example, in the case of a buried rupture, does not necessarily weaken the tsunami generation, but actually in some cases may even strengthen it. And this is demonstrated by these two examples showing on the top. So with the same identical and simple subduction zone geometry and configuration, but with this different distribution of the rupture, one with a trench breaching slip, the other with a buried slip. And the two has the same peak amount of the fault slip and same width, but one is on the shallow part and allows the slip to go all the way to the trench. And because of this difference in their slip distribution, we see a different surface deformation pattern here. And this trench breaching case is associated with a large contribution of the horizontal motion of the sloping seafloor, as shown by this gray area here. But because in the buried rupture case, there are a lot of enhanced elastic thickening in the upper plate, and also a lot of shear deformation of the upper plate here. It really helped to form this big bulge on the seafloor. And subsequent tsunami simulation also indicated that this is a case that will generate a higher tsunami run-up. And actually, not just because of the highest uplift on the seafloor, it is the entire shape of the surface deformation, the wavelength and the gradient from the peak uplift and to the peak subsidence here, and the location of those peaks that determine the tsunami-genic potential of these different types of slip. And if you haven't checked this paper yet, I would strongly encourage you to take a detailed look at it. So back to the shallow soft barrier. There are a lot of mechanisms, various mechanisms may contribute to this type of behavior. And on the top of the list is the velocity strengthening behavior of the shallow fault, which has been confirmed by a lot of laboratory experiments by conducting frictional experiment on the rock samples retrieved from the shallow part of the fault, typically from ocean drilling expeditions. And also very important is the fault roughness and heterogeneity in terms of both the lithology variation and also the structure complexity. And the ultimate effect of this roughness and heterogeneity is that they will make this localization of the shear onto a thin fault plane very difficult over a wide range. And this is a necessary condition for fast seismic rupture propagation to go through. And especially if we consider that the shallow part of the fault is the place where some of the fresh new roughness is freshly introduced in the subduction system. And also the wall rock properties, for example, the consolidation state of the upper plate may also be very important. The frontal part of the upper plate wedge is typically composed of the less competent and low rigidity materials, which make them less favorable for elastic strain accumulation. And this idea has also been adopted to explain some of the along strike variations in the megathrust behavior. And also fluid-related processes, for example, high fluid pressure and dilatancy strengthening can be also very important. And some other work has indicated the importance of some other mechanisms, for example, the ultra-slow fault healing on the shallow fault. So then, how would this shallow creep continue to evolve in the post-seismic toward the interseismic phase? We think that two mechanisms are very important. First is the prolonged afterslip. And the aseismic shallow afterslip would continue for some period and continue to release the coseismic increased fault stresses on the shallow part of the fault. And geodetic observations has indicated that for some earthquakes around the world, we can have this duration of afterslip by many, many years. And it's hard for us to fully resolve the total duration because some of the decaying signals near the end can be beneath the detection threshold of modern day geodesy. And the other important mechanism is the leaky stress shadow. And in this case here, it is important for us to realize that the upper plate is not a rigid block. So it can host elastic deformation. And while the loading is applied to the deeper part of the megathrust, the continued ongoing elastic deformation of the overriding plate would allow liquid stress to be imposed on the shallow part of the fault, and then to drive the shallow fault to creep in the interseismic phase. So over the long time, there is a balance between the stress leakage onto the shallow fault and the ongoing creep at a constant rate to remain a constant stress state of the shallow fault. But in reality, the shallow creep here may be in the format of episodes of slow slip events or bursts of slow earthquakes, and they probably allow the stress state to fluctuate around some degree. And this leaky stress shadow is actually not something new. And from the numerical simulation conducted by a number of authors, we have seen that with this stress shadow, we are able to see partial creep updip of the seismogenic zone, of the locked seismogenic zone. And the greater the distance from the locked zone, the faster the creep it is. So we can imagine that this rate of the shallow fault creep inside of this zone here is also dependent on the width of this updip zone. So if for a wider updip zone here, we will tend to have a faster creep within it. And the transition from this between these two mechanisms here from 1 to 2 should be a gradual process. But we do expect that it will be faster transition for a narrower updip zone, and which also correspond to a slower fault creep inside of this zone here. So to demonstrate this idea, we have conducted some simple rate and state friction modeling experiment. And in this case here, we use a very simple fault geometry, and we assume a constant critical slip distance d sub c and an effective normal stress on the fault to make the model as simple as possible. But the two cases here are showing two different widths of the shallow velocity strengthening zone relative to the velocity weakening zone. And in this case here, we can see that this difference in terms of the width of these two zones would cause a large difference in the pattern of the coseismic and interseismic slip distribution. In the right-hand side case, with a very narrow updip zone, the soft barrier at the shallow part is not able to fully resist the coseismic rupture. And we see a large coseismic rupture breach the trench, followed by some very minimal amount of aseismic afterslip. But in the case of with a wider updip zone, we see that this post-seismic or interseismic creep can last for a very long duration. And those contours here, each of the black contours here shows the slip distribution of every 40 years. And we can see that even after a long time, more than 100 years, we are still seeing the slowing down of the creep rate. So this is the effect of the prolonged afterslip. And by the end of the interseismic phase, this creep rate here in this wide updip zone case is much faster than this narrow updip zone case. So in the real world, all the subduction zones will fall into the transition between these two cases, or maybe even more extreme than shown here. So now I'm going to show two end-member scenarios for this kind of leaky stress shadow concept. The first investigations from JFAST and JTrack has helped us to understand the mechanism for this large trench breaching for slip here. And we see that the fall zone rock here is very clay rich. And so it can dramatically drop its frictional strength at this high rate shearing. And also there's a large contrast between the weakness of the clay rich fall zone and the upper plate material strength. And this kind of configuration would allow this shear, plate boundary shear, to quickly localize onto a very thin fall zone to sustain this rupture propagation through the shallow part. So post-seismic deformation and its interpretation is consistent, is compatible with the idea that there are minimal amount of after slip in the central area here. And in fact, for these two patches here to the south and to the north, we found that in order to explain this deformation, the duration of the after slip has to be very short, has to be within 10 years. I'm not showing the detailed spatial temporal variation of the afterslip distribution here, but it is something we are currently preparing in a manuscript to be submitted very soon. So please stay tuned for that. Another perspective to look at this is to look at the evolution of the locking degree of the fault. And we found that in order to explain the later part of the seafloor displacement here, for example, after year 5, since this big event, we need to include this locking effect as shown here. So with the locking distribution shown here and the effect of the surface deformation shown by those blue vectors. And we found that this locking effect is actually also very consistent with the GNSS velocities, both on onshore and offshore before the Tohoku-oki earthquake. So this is an indication of a very rapid relocking or recovery of the locking degree of the Japan Trench megathrust within a duration of less than 10 years, considering the quick dissipation of after slip distribution as well. So this is a one end member case. So let's now go to another end member case. And this example here is from the Costa Rica earthquake. And it is to do with the 2012 magnitude 7.6 megathrust event. And in this case here is a much smaller event and buried to a deeper part of the megathrust. And this central part of the North American, this part of the Central American Trench here can host a magnitude 7.5 or above events at a rough recurrence interval of every 50 years, as some of the previous events shown here. And here we have a very high sensitivity tool for us to investigate this shallow fault slip. And this tool is the deep sea borehole fluid pressure monitoring. And the idea is to use the pore fluid pressure as an indicator of the volumetric contraction or dilatation. So with contraction here, we'll see fluid pressure increase. With dilatation, pressure will drop for less drained, undrained scenario. So after this 2012 event, what we see here is that over some period, we see these episodes of opposite pressure variations on these two sides, indication contraction on one side and dilatation on the other side. So this is an indication of that the fault slip has to propagate to the shallow part of the fault. Because if they are far away, we would see the same response on the two sides. And here, I didn't say that we have these two boreholes here located on the two different sides of the deformation front. So they are kind of seeing this response on the two different sides of the fault. And also at the same time, because we also measure seafloor pressure at these two borehole sites, by using the seafloor pressure on the incoming plate as a reference, so we can see this pulse-like uplift pressure change, seafloor pressure change on the prism toe side, which is an indication of this pulse-like deformation and uplift of the prism toe. And then over a certain period, we can use this total uplift of the frontal prism and treat it as a geodetic measurement. And together with those onshore GPS displacement to do an inversion to infer the afterslip distribution. And despite the large uncertainty along the strike, but locally near the boreholes, we are confident that there's a large trench breaching afterslip to the trench. Unfortunately, we do not have data from those boreholes after the year 2013. But fortunately, the records were there before this event, which essentially provide a window of the late interseismic phase of the previous earthquake cycle. So in this case here, we are seeing this recurring shallow slow slip events with clear evidence of the fault slip goes all the way to the trench. Again, here, for those two examples here, 2007, 2009, we are seeing this opposite sense of pressure variation in the formation and also this change in the differential seafloor pressure on the two sides. So this is an indication of the slip breaching, trench breaching and slow slip before the event, some recurrence interval of roughly 1 to 2 years. And this is also consistent with the broader picture captured by GNSS measurements over the past 2 decades. So here we are seeing this very regular shallow SSEs before the 2012 event. And then after the event, we are seeing some more frequent occurrence of this SSE. And then after some period, return back to the roughly regular SSE recurrence. So this is an example of a very leaky stress shadow. And there has to be a lot of stress communications between the deeper creeping zone and the shallow part of the fault. And plus probably some 3D effect, because we can imagine some of the creep to be in the along strike direction can contribute to this stress leakage to the shallow fault here. So in between these two end member cases, Japan Trench and Costa Rica, is there any case in between? And we think there is. And now let's move our eyes back to Japan, but to the Nankai trough part, excluding the Kyushu part, which is dominated by creep at all depths. But for this area here, about 80 years after the 2 magnitude 8 above events, we are seeing a lot of, and with the help of seafloor sensors, for example, DUNET, we are seeing a lot of abundant shallow, slow earthquakes. And we think this is an expression of the Megathrust creep today since those 2 events. And same as the Costa Rica case, here we have a transect of 3 boreholes here as a legacy from the landmark IODP expedition Natural Seas. And those formation pressure data recorded by those boreholes here provide us an important record to interpret the history and the evolution of the shallow slow slip events. And overall, taken integrated over this more than 10 years, we found that those shallow slow slip events can accommodate between 30 to 55% of the plate convergence rate. And a recent work indicates that those pressure data can be used to investigate the fine details of the propagation and the nucleation propagation of the shallow slow slip. And here we see that there's all these things has been occurring in the up-dip zone of about 40 kilometers wide. This is a good size for this shallow up-dip zone to allow some stress leakage into the shallow part. Even though we cannot fully rule out that the afterslip of those two events can be prolonged for a very, very long time, even until today. So maybe some of those we are seeing here is still due to the very prolonged afterslip of those two. And is there a good example for this lower case here? Yes, we think there is. And this is present day Cascadia. So in just a few days, it's going to be the 326-year anniversary for the 1700 magnitude 9 Cascadia earthquake. And today, despite the many efforts to searching for the shallow, slow earthquakes, there's a remarkable absence of those kind of event in comparison to Nankai. And even though some local area seems to show some suspect tremor signals, but nothing has been confirmed yet to be on a shallow megathrust. So this is the case that indicate a very unleaky stress shadow. And this is also consistent with some preliminary seafloor GPS observations, which suggest that the shallow part of the Cascadia fault here of Washington and Oregon is dominated by shallow locking of the fault. And there has been more seafloor GPS sites deployed on the Cascadia subduction zone. So in not too long, we are going to see a more complete picture of this locking distribution. So I'm getting close to the end of my talk. How I'm doing with my time? I think I'm still doing fine. So I'm going to show one last example here. And this example, again, is the deep sea borehole fluid pressure observation. And it is from this site here, hole 1364A, at a distance about 20 kilometers from the deformation front. So what we see from this borehole site here is this consistent and long-term formation fluid pressure increase over the past decade. The early part of this, we can see this kind of decay rate of the pressure increase. And this is because of the formation recovery from the drilling disturbance. But I want you to focus on the later part of the pressure trend here, which is more or less linear and shows this persistent increase of the pressure. And we interpret this as a volumetric strain accumulation associated with the megathrust locking. So with some understanding of the local formation property here, we can translate this pressure trend, this pressure gradient here, into this persistent volumetric contraction rate. And in order to explain this long-term pressure increase and contraction, what we need is to assign a high locking degree, as shown here, to the shallow part of the megathrust. So with this, essentially, we are producing lateral compression of the frontal wedge and to produce this contraction signal. And actually, to better explain the magnitude of this contraction here, we even need to allow the locking degree of the shallow fault to increase slightly to the fault, as shown here. So this can better explain what we see from this borehole record. So this is an indication that the shallow part of the fault of the Cascadia megathrust here has a very minimal or little stress shadow, which allows no stress leakage to be imposed on the shallow part. It means that the shallow part of the fault is actively participated in the energy accumulation for future event. So I want to conclude with some of those points here. And we have discussed that the seafloor geodesy has widely detects shallow aseismic creep, including afterslip following large subduction earthquakes. And I show that shallow megathrust typically acts as a soft barrier to the earthquake ruptures, but a large trench breaching rupture can still happen. And we talk about the two important mechanisms to govern the evolution of the shallow creep. One is a prolonged afterslip, the other is a leaky stress shadow. And we also go through some end member and representative cases to demonstrate the control of these two mechanisms here. For example, we show that the comparison or contrast between Nankai and Cascadia can be in terms of their abundance or rarity of the shallow slow earthquakes can be explained by these two mechanisms. And I want to emphasize that this leaky stress shadow is a global phenomenon, and margin-specific factors can control how leaky this zone is. And in addition to the call for more seafloor geodetic observations, another important thing point to make is that the trench breaching is not a necessary key ingredient for tsunami generation. We show that buried ruptures can also be very tsunami-genic. So here is a list of references for the examples I shown at the very beginning of my talk about this distribution of slow, all the different types of slow earthquakes around the world. So I think I'm going to stop here, and I'm happy to take any questions. Thank you.
Thank you so much for such an excellent talk. As Tian just mentioned, we can take questions. So if you want to type those in either the chat or the Q&A feature, go for it. We already have a question from Keelan in the Q&A section. Keelan says, re Tohoku locking, can you elaborate on how and why current GNSS vectors on land moving seawards are different from those before 2011 moving landwards, despite the similar locking distribution?
Can I see the question again? I'm sorry, or is that?
It's on the Q&A.
It's on Q. Okay, I see. Oh, Kelly, how and why the current GNSS and long land moving are different from those before, despite. Yeah, okay, yes, probably I didn't elaborate. So for the current GNSS, it also affected by the post-seismic deformation of the Tohoku-oki earthquake. But before the earthquake, it's predominantly by the locking effect only. So I think the difference is caused by the ongoing viscoelastic relaxation, which will last for many more decades. I think that's yeah. So probably I didn't explain that part, yeah. But despite the ongoing viscoelastic relaxation of this earthquake, we are still seeing that the locking pattern on the megathrust appear to be quite similar before and after the earthquake.
Great, thanks. We also have a question from Akhtarul Asan, who says, what happens if the subduction has migrated to the land side, not in the ocean anymore?
Oh, so yeah, more talking about the I think okay, not in the ocean anymore, so more in the continental environment. I think that's something, and the question here is a bit broad. I think in that case, it will be much easier for us to deploy GNSS, right? Because we can just deploy the GNSS or even some other tools directly on top of the fault. I think that's a good thing, but I'm not sure what is the main focus of the question here. Does the shallow fault still behave the same? I'm not too sure, but I think from some of the continental faults, and some people here knows better than me, is that the shallow part of the fault also tend to behave aseismically. So even not beneath the ocean, the shallow fault may still, because of a less consolidated state, and may also behave in this way. But it will be a very different environment, I would say. Yeah. Good question. I didn't think too much about this though.
Thank you so much. We still have some time if anyone else has any questions. I'm not seeing anything new in the chat or the Q&A feature. But if you think of a question after, feel free to email us and I'll make sure that Tian gets it. Or feel free to email him directly. I'm going to give everyone a couple more minutes just in case someone is typing. But thank you so much for such an excellent talk.
Thank you.
Okay, I have one more question, again from Arturo Sun. If the clay in the shallow part of the megathrust is old, will it still behave as a slipper to creep?
I feel this question is I'm not too sure how old is the clay. I think some of those are pelagic clay that deposition in the case of Japan Trench. So in that case, this clay zone is very weak and it allows a large coseismic weakening to happen to slip the trench. So yeah, but I think it's so. I think the point what I kind of wanted to make is that it's not just about the fault zone material itself. It also to do with a lot of other things. For example, the roughness of the fault zone. And also maybe it has to do with the upper plate material properties. So whether the shallow part behave as the aseismic zone or tend to join the coseismic rupture is dependent on those multiple factors altogether, and together they may create a condition for the fault to behave in one way, not the other. Yeah, I'm not sure if I fully addressed this question, but that's my thought for now. I'll be happy to have more detailed discussions on this.
Yeah, Arturo, if you want to send an email, feel free to do so. I'm not seeing any more questions in the chat, so I think we're going to give people back the 15 minutes left in the hour. But just so everyone knows, this talk will be recorded and put up on the YouTube channel if you want to share it with your friends or colleagues. And as for always, if you have any other suggestions of speakers, please let us know. We're happy to listen to the wants and needs of the community. So without further ado, thank you so much for giving this wonderful talk and for taking the time to join us today. And I hope everyone has a great rest of your day.
Thank you.
Thank you.
Thank
Bye.
you. Thank you, everyone. Bye-bye.